Today, I would like to present a practical guide to HPLC columns for building robust methods. The outline of the presentation is as follows. First, we'll look at column type and phase selection. We'll then explore differences in particle sizes and how they affect chromatography. We're going to look then at column ID and length, and finally, the effect of particle pore size on the chromatographic separation. Column type and phase selection. We'll begin with first choosing the right column. We've kind of broken this down into two major sections based upon molecular weight of the analyte or target separation. In the upper case, we have the lower molecular weight analytes or compounds of less than 5,000 molecular weight. We then look at the solubility characteristics of those compounds. Are they water soluble? If so, then we have reverse phase, ion exchange, Hillick, and SFC available as a separation mechanism. Finally, if you would look at reverse phase, we would have a number of different products available for that, along with ion exchange, Hillick, and SFC. If a molecule that's less than 5,000 molecular weight is organic soluble, then we have available for separation reverse phase, normal phase, non-aqueous size exclusion, and SFC. And again, we do have products in the various categories, such as reverse phase products, normal phase products, and non-aqueous size exclusion products. Finally, in the category of less than 5,000 molecular weight, we have a separate category of chiral separation. And these chiral separations can either be normal phase, reverse phase, or utilize SFC. If we are greater than 5,000 molecular weight, then we break down to water soluble, and there we have reverse phase available, utilizing wide pore materials and columns, and these would be products such as Macrocept Bio or Macrocept Bio Gold. In the high molecular weight category, above 5,000, we also have organic soluble molecules, and these would be generally polymer type molecules, and these again can be separated or analyzed using reverse phase or non-aqueous size exclusion. Again, this breaks down to reverse phase products as well as size exclusion products. One of the areas that we try to focus on is the development of alternative chemistries. In this slide, we could see that the C18 is at the center of the square, which is one of the major workhorse reverse phase HPLC columns utilized for separation. However, we have developed a number of specialty phases or selective phases. Again, you have the hydrocarbon-based phases such as C8 and C4, but we have phases that are suitable for high aqueous separation. Then we have aromatic-based phases such as phenyl, naphthyl, diphenyl, biphenyl, phenylhexyl, and then we have fluorinated phases such as pentafluorophenyl or perfluorinated octyl. And then we can look at the Hillick mode. We have several selective stationary phases available there, including Hillick POH, Hillick that's based on a fluorinated chemistry, Hillick FL, and the Hillick based on a organic amine referred to as Hillick PI. And then we have more of the conventional Hillick phases such as cyano and diol and amino. We could see a comparison of two chromatograms, one separation done on a C18 column, and this mixture contains 4 components. Unfortunately, we are only able to resolve 3 of the 4 components with a coelution of components 3 and 4. However, if we go to an alternative chemistry, in this case pentafluorophenyl chemistry, we're able to get a separation of all four compounds, all baseline separated and well resolved. Again, showing the strength of changing stationary phases in order to affect a particular separation. These are some examples of applications for alternative chemistries, including a separation of food additives using phenylhexyl, a separation of phenoxy acid herbicides using a perfluorinated octyl, a separation of difluorophenols utilizing a pentafluorophenyl stationary phase. In each case, the alternative stationary phase provides a superior separation that would be achieved from a traditional C18. What we try to utilize when we are taking advantage of selective stationary phases is different possible interactions in reverse phase chromatography. Generally, C18 and C8 and C4 columns or stationary phases rely on hydrophobic or van der Waals or dispersive interactions. However, we would like to utilize other interactions such as dipole-dipole, which can be seen in cyanotype columns, pi-pi interactions, which can be seen in the pentafluorophenyl, as well as other aromatic stationary phases, as well as ionic interactions. Again, with most separations, there's no pure interaction, and usually analytes or target separated molecules will experience these interactions in combination. What are the typical characteristics of an HPLC column? We've kind of broken it into two major categories. We have HPLC columns that are utilized for analytical applications, and these columns are generally from 50 millimeters to 250 millimeters long. They have column IDs from 2.1 to 4.6 millimeters, and they contain particles that are greater than 2 micron and generally top out at about 5 microns. However, we could have a fixed bed column that would be utilized for preparative chromatography, preparative HPLC, and these column dimensions would typically be length from 50 millimeters to 250 millimeters. But the difference would be the column ID. This would be significantly greater for the preparative column. Typically, these column IDs range from 10 millimeters all the way up to 50 millimeters. And again, the particle size range begins at generally 5 micron and can be extended up to 20 micron. Again, the quality of the HPLC column is dictated in a large part by the quality of the column hardware utilized, both for analytical and preparative chromatography. Now let's explore the influence of particle size on HPLC separation. This slide shows the evolution of the HPLC particle sizes and the pumping systems that were available at various times. Early in the history of HPLC, the particles were rather large, and they ranged up to 50 micron, and they were in regular type silica. This was not a particularly challenge for the pumping system, which were only able to pump up to about 200 bar at the time, or 3,000 psi. But as silica technology and column technology improved, the particle size was reduced, and we could see that in the late 80s, particles had gone down to 10 micron from the 50 micron, but we required HPLC to operate at a higher pressure, in this case up to 400 bar or 6,000 psi. So we could see the particle size progress until we achieved the sub 2 micron particle, which was introduced in about 2012. And this requires a much higher pumping system capable of pressures up to 1240 bar or 18,000 psi. Again, a larger overview is what particles match to what particular HPLC technique you're utilizing. In the case of preparative LC, the particles that are generally utilized range from a low of 5 micron to a high of 20 micron. For traditional HPLC, particle sizes range from 3 micron up to 10 micron. And with the introduction of UHPLC, we are now able to utilize particles of sub 2 micron, or in this case, 1.8 micron particles. We can examine the effect of particle size through the Van Deventer equation, which is shown in this slide. There are 3 major contributions to the Van Deventer equation. We have the A term, which is the Eddy diffusion, the B term, which is molecular diffusion, and C, which is mass transfer. The input, in order to develop the Van Deventer equation, in order to plot the results of the Van Deventer equation, involved the varying of linear column velocity, and then measuring the H, or the height equivalent to a theoretical plate, in other words, the peak sharpness. The linear velocity is based on the use of a void marker. So how does flow rate relate to particle size? Well, generally, smaller particles yield lower HETP. In other words, we have a higher efficiency per unit length. The optimal flow rate range is greater with smaller particles. Smaller particle columns have less efficiency loss at higher flow rates. In other words, the height equivalent to a theoretical plate does not change very much as we vary the flow of a smaller particle column. Let's now explore each of the factors of the Van Deventer equation. First, we'll start with the A term, or the Eddy diffusion term. This is also referred to as the multi-path effect. And we can actually see in this diagram the idealized particles shown here in red, and that we can have an analyte stream through different paths of this particle bed, with the analyte taking the fastest path, generating the 0.1 of the peak. An intermediate path generates 0.2, followed by the longest path of the diagram of 0.3. So we could see varying paths of the analyte molecules will generate the actual peak shape, or the width of the peak. The main factor here is we decrease particle size, we also decrease the multipath effect. So we do get sharper peaks just based on the Eddy diffusion term by utilizing smaller particles. Another term of the Van Deventer equation is molecular diffusion. And this is really independent of particle size. And this is really related to the actual operating flow rate of the HPLC column. We could see 2 columns, or 2 idealized flows, shown in this slide. The upper column has a much higher flow rate, and the band is much sharper. The column on the lower column has a wider band and has more of a spread. The molecular diffusion term is generally not a factor in normal chromatography. It only comes into play at very low flow rates. The most significant term that's affected by particle size is the C term of the Van Deventer equation, or the mass transfer term. C decreases with particle size so that the slope of C times the linear velocity also decreases with particle size. And we could see this effect of the C term shown in the graph here. And this is one of the biggest factors that's involved in utilizing smaller particles. So if you have a smaller particle, you'll have better mass transfer of the analyte from the stationary phase to the mobile phase, and you'll consequently have sharper peaks over a longer flow rate range. Influence of particle sizes. There are a number of advantages to utilizing smaller particles. They do reduce diffusion. They increase efficiency and resolution. They do provide for higher sensitivity, higher peak capacity, and reduce the influence of flow on the separation efficiency. Higher optimal flow rates allow for faster analysis. There are some disadvantages of smaller particles, including increased back pressure, the need to have an upgraded or optimized HPLC platform in order to utilize the performance of the small particles, and finally, greater demands on column hardware. And this is just one example of the importance of utilizing an optimized system when using smaller particles. In the upper chromatogram is a non-optimized system, which has a dead volume of 22 microliters. And we can see that the peaks, when compared to an optimized system with a volume of 12 microliters, has a less of a separation capability, a lower resolution factor, and broader peaks. So it is extremely important that when utilizing small particles, that the HPLC system must be optimized, which includes the injector, the tubing sizes, the detector cell, and the data system, in order to fully utilize the potential of small particle chromatography. Again, this is an example of the typical efficiency gain of a mixture of neutral compounds run on a 3-micron column versus a 5-micron column. We could see that we have an efficiency of 18,000, almost 19,000 plates on the 3-micron column, where we have an efficiency of the 5-micron column of about 14,000 theoretical plates. And again, referring back to the Van Deventer curve, where the smaller particles have a wider flow rate range in terms of maintaining a sharp peak sharpness, we could see an example here of a 3-micron versus a 5-micron column. With the 3-micron column only experiencing a 9% loss in efficiency as we change the flow rate from 1 milliliter per minute to 1.5 milliliters per minute. However, if we perform the same separation utilizing the 5-micron column, we have a loss of 15% as we go from a 1 milliliter per minute flow rate to a 1.5 milliliter per minute flow rate. As I have mentioned earlier, there are some significant advantages to going to smaller particles, particularly sub-2 micron particles, and the factor that we're able to operate at a wider optimal flow rate range. We could see that these, in this case, Van Deventer curves again, but we could see the plot for the sub-2 micron or the 1.8 micron column has not only is more efficient or has a lower height equivalent to a theoretical plate, but it maintains a lower height equivalent to a theoretical plate over a wider range of linear velocity, even when compared to a 3-micron column. Again, this flow rate range is almost double the optimal flow rate range of a 3-micron column. Smaller particles equal higher efficiency and better resolution. Efficiency is inversely proportional to particle size. And we can see a chromatogram or a peak here that's 1.8 versus a peak generated by a 5 micron column. The 1.8 micron column has 142,000 plates per meter, while the 5 micron column has 75,000 plates per meter. And we can see how it affects the resolution. The 1.8 micron column has baseline resolution of the two components, while the 5 micron column does resolve the two components, but not in the baseline fashion. The main advantage of utilizing sub-2 micron columns is the advantage, again, of maintaining the separation at very high flow rates. In this case, we can take a separation that's performed on a 5 micron, 15 centimeter, 4.6 column, utilizing a flow rate of 1,000 microliters a minute or 1 mil per minute. It operates at a pressure of 80 bar. But in order to effect the separation, it takes about 27 minutes and utilizes 27 milliliters of flow. However, if we utilize a sub-2 micron column, we're able to shorten the column to 50 millimeters, narrow the diameter to 2.1 millimeters. It operates at a flow of 600 microliters per minute, and it uses 1.8 milliliters of total flow and performs the separation in 3 minutes. However, the operating pressure is 500 bar for the sub-2 micron column. What are the overall advantages of sub-2 micron HPLC columns? First of all, we have improved speed of analysis, better chromatographic resolution, which can provide better sample insight and more peak capacity, better sensitivity, which can improve impurity tracking, generates taller peaks, and can require lower or smaller injection volumes. Better mass spec compatibility because of the lower flow rate requirements. And finally, because of lower solvent consumption, the smaller particle columns are greener. Smaller particles have a greater optimum flow rate range. Smaller particles reduce the influence of flow on the separation efficiency and allow greater optimum flow rate ranges. An analytical column with a 3 millimeter ID has a flow rate range in the sub-2 micron format of anywhere from 0.5 to 1.2 milliliters per minute. However, if we increase the particle size to 3 micron, we now narrow the flow rate range from 0.4 to 0.8 mils per minute. And again, if we raise the particle size to a 5 micron, we further reduce the optimal flow rate range. And in this case, we're operating from 0.3 to 0.5 mils per minute. Now let's look at the effect of column dimension, including column ID and length. Longer column equals higher efficiency and better resolution. Efficiency is directly proportional to column length. In this slide, we can look at the effect of column length. We do have higher plates per meter with the shorter columns because of packing efficiency effects. But in terms of plates per column, the longer column, the 250 millimeter column, shows about 20,000 plates per column, where a 100 millimeter column has about 9,000 plates per column. And again, this has a direct effect on resolution. So with the 100 millimeter long column, we have a resolution of peaks 4 and 5 of 7.36. However, with the 250 millimeter long column, we've now increased our resolution of peaks 4 and 5 to 10.1. There are some advantages to increasing column length. You do increase retention, and you do get better separation, increased efficiency, and resolution. However, there are a number of disadvantages to increasing column length, including longer analysis time, greater solvent consumption, increased back pressure, greater costs for the column, and lower overall efficiency in terms of plates per meter. A better approach might be to decrease the particle size to increase efficiency, or to decrease column ID to obtain a quicker separation. A better approach to increase efficiency, again, is smaller particles. And again, efficiency is inversely proportional to particle size, and efficiency is directly proportional to column length. So it might be better, in order to increase the resolution of separation, to utilize a smaller particle column rather than a longer column. The benefits can be greatly enhanced through the use of smaller particles. Now let's look at the influence of column ID. Smaller diameter columns, such as 2 and 3 millimeter ID columns, are greener because they utilize lower flow rates. They experience less radial dispersion, which enhances detector sensitivity. They are readily compatible with LC-MS, and they generally require smaller injection volume. However, there are some disadvantages to smaller column IDs, including lower sample capacity and the requirement of an optimized HPLC instrument for narrower columns. Here's an example of how the smaller column ID can provide for greater sensitivity. There's a comparison of two chromatograms, one performed on a narrow bore column of 2.1 millimeter ID versus a conventional column of 4.6 millimeter ID. We could see that we get approximately a 5-fold increase in sensitivity by utilizing a smaller bore column. Higher mass sensitivity is achieved due to less sample dilution from the smaller column volume. Smaller ID equals a lower solvent consumption. In the column format of 4.6 millimeter, the solvent consumed in 5 20-minute runs is 100 mils per minute. However, if we reduce the column ID to 3 millimeters, we reduce the solvent consumption from 100 mils per 5 runs to 40 mils, or a 60% saving in solvent. Finally, if we reduce the internal diameter to 2.1 millimeters, the solvent consumed in 5 20-minute runs is 20 mils. This represents an 80% reduction in solvent. Again, we can look at the flow rate ranges for the various column IDs that are utilized, including the 2.1, which has a flow rate range of 0.2 to 0.5 mils per minute, and has a typical sample capacity of anywhere from 100 to 500 micrograms, and a relative mass sensitivity of 5. If we now go to the larger internal diameter, such as the 3 millimeter, the flow rate range is from 0.4 to 0.8 mils per minute. Our sample capacity is increased from 200 micrograms, between 200 and 1,000 micrograms, and the relative mass sensitivity is 2.4. If we use the conventional 4.6 millimeter ID columns, the flow rate range is typically between 1 and 3 mils per minute. The typical sample capacity now is increased and is from 1 to 5 milligrams. And again, this is just represented by a relative mass sensitivity of 1. So again, we do get a 5-fold increase in relative mass sensitivity by utilizing the narrow bore 2.1 millimeter ID column. We can look at a range of flow rates for different columns IDs, including 2.1, 3, 4.6, 10, 20 millimeter ID column, and 30 millimeter ID columns. And again, for 5 micron particles, the flow rate ranges anywhere from 0.2 mils a minute, the optimal flow rate, for a 2.1 millimeter column, all the way up to 42.5 milliliters per minute for a 30 millimeter 5 micron column. Then if we're going to convert from conventional 4.6 millimeter ID columns to 2.1 millimeter ID columns, we can not only change the length and the ID, but we can also change the particle sizes. So we can get an equivalent separation. Instead of utilizing a 150 by 4.6 millimeter 3 micron column, we can optimize the separation using a 50 millimeter by 2.1 millimeter column containing a 1.8 micron particle or a sub 2 micron particle. And the same effect occurs if we need to reduce from a 5 micron particle that's contained in a 250 millimeter column of 4.6 millimeter ID. We can reduce that by utilizing a 100 millimeter column with a 2.1 millimeter ID, and again, utilizing the 1.8 or the sub 2 micron particle. Now let's take a look at the effect of particle pore size. Particle pore size, we could see typical particles anywhere from 1.8 to 5 would contain pores generally between 60 and 1200 angstrom. The bonded phase is actually bonded to the surface and is contained within the pores of the silica particle. A silica particle generally has a range of pore sizes, generally 60, 80, 100 angstrom, 120, and so on, all the way up to 1200 angstrom. What is the influence of pore size on the separation? Surface area is inversely proportional to the pore size. Generally, higher surface area silica have smaller pores. Most interactions between the analyte and the stationary phase occur within the internal pore structure of the particle. If pores are too small, large molecules cannot access the stationary phase. If the pores are too large, greater than 1,000, then the silica particle becomes fragile. And we could see an idealized diagram of a large pore versus small pores shown on the right portion of the slide. Again, we could see here on this slide how analytes can interact with the various pores. In this case, the analyte is larger than the pores in the 100 angstrom case, and these analytes cannot interact effectively with the stationary phase contained in the pore structure. However, the analytes are well suited to interact with the 400 angstrom pores, generating a much improved separation. Small pore particles, for molecules less than 5,000 molecular weight, pore sizes usually range between 60 and 150 angstroms. with a majority of the pore sizes being between 80 and 120 angstroms. Pore diameter is usually not a primary consideration in terms of separation of lower molecular weight compounds. However, there are cases where selectivity can be improved and separations can be affected when a 60 angstrom pore size is utilized. Wider pore particles are available in sub 2 micron, 3, 5, and 10 micron particle sizes. They are utilized for molecular weight ranges from 5,000 to 100,000 molecular weight, and in that case, the 400 angstrom pore particle would be ideal. If we go to larger molecules, greater than 100,000 molecular weight, then those particles are available as 3, 5, and 10 micron. And again, in the case of the 1200 angstrom, we can utilize that for the analysis of a 100,000 molecular weight molecule. In summary, we've provided alternative column selectivities for rapid method development. Smaller particles yield higher efficiency separations. Smaller column ID allow for greener methods. Longer columns provide higher resolution. Pore size is important for large molecule analysis, but is not a primary consideration for the analysis of small molecules. And with that, I would like to thank you for your attention.